This is a presentation for SENeCA, our scalable, energy-efficient, neuromorphic computer architecture. The goal of neuromorphic engineering is to build energy-efficient computers that behave like biological brains. Therefore, here in SENeCA, we decided to include some interesting features like sparsity exploitation, data flow parallel processing, which is scalable, processing on low precision parameters, asynchronous and non-deterministic processing, and adaptivity. SENeCA is designed by connecting many neurosynaptic cores with each other through a network on chip. In the network on chip, the spikes moves and reach to the destination neurosynaptic core, which acts as a time multiplex axons in the biological brain. Inside each neurosynaptic core, we have also time multiplex physical neurons, which emulates many neurons in the algorithm. To harmonize the time multiplex process, we need a controller. And in SENeCA, we use a RISC-V based controller to improve flexibility of the system. This slide shows the internal architecture of a neurosynaptic core in SENeCA. It contains a RISC-V based controller, which we use IBEX from OpenTitan as a low overhead flexible controller. It includes axon message interface to accelerate event filtering and flow control. It includes a shared memory prefetch unit to allow accessing to the shared memory, which is outside of the core. It contains 8 NPEs, which are the physical neurons and are time multiplexed to emulate several hundred or thousand neurons. They are designed to exploit sparsity. They are designed to use different data types like 4 bits, 8 bits, and 16 bits for different parameters. And we can program the neural model and learning rule for these physical neurons. The event capture unit here accelerate the event generation, which are coming from spikes from the NPEs. The loop buffer is a small memory which stores the neural model and is programmable. The network on chip is a unit that connects the neurosynaptic cores with each other and is able to perform multicasting with source-based addressing and also compression. Here we show the synthesis result in Global Foundry 22 nanometer FDXOI. And for example, it shows that the IBEX core only consumes 4.2% of the total area of the core. We also provide software development kit for SENeCA, which at this moment includes a toolbox to convert conventional DNN models to SNN, a behavioral SNN simulator, a hardware-aware SNN simulator, a hardware mapper, which maps the SNN models to the cores in the hardware, and the automatic code generator that receives the mapped version of the model and then generates the binaries for the hardware. A hardware-aware simulator can help mapper in finding the best mapping for energy and latency efficiency, and also it can be used for other type of architecture exploration to find, for example, in this picture, the best shared memory bandwidth for latency of the system.